This is a video of momentum and impulse. Linear momentum is conserved unless the system experiences an outside force. If the system experiences an outside force, then the change in the system's momentum can be calculated by the amount of force applied to the system multiplied by the time in which the force is applied. This is called the linear impulse. Therefore, the linear impulse is equal to the change in linear momentum. Okay, well, that's all fine and dandy, but let's look at how that is actually applied physically. So let's say I've got an object moving at a particular velocity, and obviously it has a certain mass. If that's the case, then it's got some momentum. We'll call it our initial momentum. In order to get it moving, if there's nothing else part of the system, something else has to come outside of the system. A force has to be applied on this object, the same object, over time to get the object to be moving faster at a later time. So in other words, what we're saying is an outside force has to act onto this system made of the single object in order to get the momentum of the entire system, again made of the single object, to increase. So this block represents the initial momentum, or this box represents the initial momentum. An impulse is applied to the object, in this case the block. That impulse increases the momentum in the final situation. So as you can see, this change in momentum, see how the momentum increased from this amount to that amount? That is equal to this impulse. So the change in momentum, P final minus P initial, is equal to the change in momentum, which is equal to the impulse. And the impulse can also be calculated by taking the force and multiplying that times the time. So that's one of the ways we can calculate the impulse, by taking the force and multiplying it times the time. The units for impulse are Newton seconds, or we could use kilogram meters per second. Notice that's the same units as momentum. So impulse can also be determined by finding the area under the curve of a force versus time graph. So in this force versus time graph, this area below the line all the way down to 0 is the impulse. In this case, it's a positive impulse because it's a positive force times the time. If we don't get a flat horizontal line and we get a diagonal line, then our areas, again, between the line and 0, become the impulse, and they're triangles in this case. This area of this triangle is negative because this is a negative force times the time. This impulse from this area is positive because that's a positive force times the time. Because they're triangles, remember, we're going to use base times height divided by 2. In rectangles, we just use base times height. So again, the whole idea there is we have to look at the areas, and positives and negatives matter. So let's look at this example. Let's say a force acts on a 1.2 kilogram object moving 120 meters per second. The direction of the force is aligned with the velocity. So this force from the exhaust is acting on the object. What is the new velocity of the object? So here's the before, the during, and the after situation. And here's a graph of the force being applied to the rocket for a certain amount of time. All right, so at the beginning, we have a certain momentum. The rocket has a mass. It's moving with a certain velocity, so this represents the initial momentum. Then an impulse is acted upon the rocket. Okay. After the impulse acts upon the rocket, it now has a greater velocity and therefore a greater momentum. Okay. So the equation we would use is this initial momentum, P sub I, plus the impulse equals the final momentum. Now the question is, how do we go about finding the impulse? Well, the impulse is represented by the area under this triangle. So we have to calculate this impulse from that area. So because it's a triangle, we got to go base times height divided by 2. So base times height divided by 2, the base is 0.1 seconds. So this goes 0.4 to 0.5. So the difference in that is 0.1. That's the base. Times the height, it goes from 0 to 2,500. Up here is 2,500. We divide that by 2 to get an impulse of 125 Newton seconds. Okay, so to finish off our math, we want to use this equation that we already came up with. Remember, the momentum in general is calculated by taking the mass and multiplying it times the velocity. So our mass at the beginning was 1.2 kilograms. The velocity at the beginning was 120 meters per second. That's the initial momentum. We applied this impulse, which we calculated out to be 125 kilogram meters per second. And then we have this final momentum, which is the mass times the final velocity. And we're looking for this final velocity. So we do the math. We figure out that this part becomes 144 kilogram meters per second. Notice that here for the impulse, I'm using kilogram meters per second. Remember that kilogram meters per second or Newton seconds can be used for impulse. Now we add up the left side of the equation to get 269 kilogram meters per second. Then we divide both sides by 1.2 kilograms to get final velocity 224 meters per second. So the object went from 120 meters per second to a final velocity of 224 meters per second. Now the important topic here is that the linear momentum is not conserved because there's an outside force applied to the system. Now it may seem like the fuel is within the system, but we're treating it as something, as a force that's being applied outside of the system onto the rocket. And that's it.